So good afternoon and welcome to the lecture today. Somehow there is something different on YouTube, so please say hi in the chat so I know you're there. It's gonna take like 30 seconds, but I think there is people viewing because I see a number of people there, but usually there is a nice graph where I can actually see how many people are there. It's not there on YouTube. I'm back on my old trusty setup, so everything should be fine today. Hopefully the volume of the sound is okay. If not, let me know and we'll adjust. So, outline for today. We're in week 7, which means that this is the last week that we will be doing new mathematics. And the topics for this week are a bit more on integration plus differential equations. What we will be doing on integration this week is actually quite insightful. We will be looking what happens if you take the graph of a function and you rotate that around one of the axes. Then you get an object and we're going to compute the area of such an object. Also, what we will be looking at is if you have a graph, what is basically the length of the graph. So if the graph would be a piece of rope, what is the length of that piece of rope? Then on differential equations, what we will be talking about is what are differential equations, and basically it's an equation that involves a function plus a derivative or multiple derivatives of the function. And also how can you solve them, where do they appear, and it will turn out that quite a few problems in daily life can be modeled using differential equations. They're very, very important. And basically, if I'm not teaching calculus, one of the main things of my job is trying to solve differential equations. If you cannot do it analytically with pen and paper solutions, can you do it numerically? Or can you do numerical techniques to solve differential equations? Now, in the meantime, I would have liked to see something in the chat here, so I'm going to update and see if anything is there, because I don't see anything yet. So I'm getting a little bit worried. Okay, so now it wasn't updating. The screen wasn't updating, but the volume is okay. Everybody's there. I see a couple of highs. Excellent, good. And also now I've got my usual YouTube graphs that show me how many people are viewing. So perfectly happy, ready to go. Excellent. So before I go to the week 7 stuff, I'll first discuss your questions, the online questions that you put in. So keep them coming. That's the most important part, I think. I mean, I like talking about the mathematics material, but above all, I prefer to treat those questions that you find difficult, because in principle, the mathematics is also in the book. You can read it in the book. I'll try to explain it here, show you applications, but I would most like to spend my time on those things that you have difficulties with. So let's go to the Canvas site, on the university Canvas site on this course. And here are the questions that are up so far. So the first question is, when do we get our corrected grade for the midterm? So the idea is that the midterm has been marked now, so you should be able to see how many points you got per question. As you know, I made a mistake because I asked something about week 4 and it will be corrected. That will be on Friday. So currently we wait until Friday. You can look at your test and you can see how it was graded. You can also put comments there, ask questions. So please do that and see where you got the full points and where you may have made maybe mistakes, or maybe there was something with the grading, so you can leave comments there. So that's open until Friday, and at Friday we will fix the marks, and then we will also do a compensation for this question where you needed the limit of sine of x over x, because we hadn't talked about that yet and I forgot about that. So the midterm, it is 100% corrected. I checked today, I did the final markings there myself. And if you have questions, put them there, and the person who marked your test, which will be your tutor, will respond to the questions that you may have there. Okay. So next one is a question about, it says question 13 of chapter 3.1. As I told you before, since I'm working at home, I have a paper copy of the 5th edition at university, but here at home I only have a digital version of edition 4. And I looked up this question, so I copied the question to my iPad. So let's switch to my iPad screen. That should be here. Yeah, excellent. And then the question that was just on Canvas, I copied it here. So it says, a company estimates that FX 1,000 software games can be sold at the price of X dollars as given in the table. So in the table you see that if the game is $20, then apparently 18,000 copies will be sold. If they make it more expensive, $30, then they will only sell 14,000. And if they charge $40, then 12,000 copies will be sold. And the question here is, say that we price it at $24. Now, obviously, $24 is not in the table. And you could say, well, I'm just going to take the average of 20 and 30. So I do have data for $20 and $30. So I'm going to take the average, but of course that is not very accurate and you can do better than that. So the main idea that you have to do here is, if you would make a graph, so say that we would make a graph and on the horizontal axis we put X and on the vertical axis we put f of X, so that's the amount of games sold. Then we have data for 20, 30 and 40. And at 20, it is apparently 18. Then at 30, it is going to be 14. And here, it is going to be 12,000 copies. Now, this is all the data we have. So we have 3 data points here. Now, the main idea is that we are going to do a bit better than just using one of these 3 values or taking the average or whatever. What we are going to do is connect those points using straight lines. So linear interpolation, if you like. So the main idea is that we will, sorry about that, in between 20 and 30, we are going to draw a straight line here. So let me just dash this a little bit further. And let's call this line here L. So L is the line. I'm going to emphasize it and say the straight line. But in mathematics, a line is a straight line. And if you have a non-straight line, you would call it a curve. So a curve is banded, a line is straight, but straight line, just for emphasis, is a straight line through. So through. Well, the 2 data points we have there. So 20, 18 and 30, 14. And what we're being asked here, if you look at the question A, is what is the amount of computer games sold? What is FX for 24? So basically we have, let's do that in black. Somewhere in between here, we have 24. And now as an approximation for 24, I am going to use linear interpolation. So I'm going to look at this straight line and see which value it gives me. So what is the equation for a straight line? Well, the slope, let's say that this line y equals mx plus b. M is the difference of y values, 14 minus 18 over the difference in x values, 30 minus 20. So that gives me minus 4 over 10 or minus 2 over 5. And then to find, so I found the slope now, I know what m is, and I would still like to know what b is. Well, how can I find b? I have two options. I know that this point here, the point 2018 is on the straight line, or I could use that the point 3014 is on the straight line. They would give the same b's, so you can choose either. What I'm going to choose here is I'm going to say that x equals 20, y equals 18 is on L, comma, so if you plug that in, then you find that 18 equals minus 2 over 5 times 20 plus b. And then if you solve for b, you find that it equals 26. I did that on a piece of scrap paper before, otherwise I couldn't do that so fast. So apparently, the red line, the straight line, has equation y equals minus 2 over 5 times x plus 26. And now if you look at the question, then the question was find the y value for x equals 24. So if you take x equals 24, then from these two we find, if you do the computation, that y is 16.4. So apparently the number of computer games sold is 16,400. And then the B question for 36, you basically do the same thing, but then you are going, let's do that in green. You will do the line through these two data points. So let's call that, I don't know, L tilde. So same question, but a different line. But the main idea for linear interpolation is that you take your data points and two data points that are next to each other, you draw a little straight line between them. So if you think about the weather forecast that you get every day, normally you get it, say, per hour. And if you would like to make a graph of the temperature during the day, what you could do is plot the temperature per hour and then draw little straight lines in between, and you will have a nice approximation of what the temperature will look like during the day. So hopefully that is clear for Jana, who asked the question. Let me switch back to Canvas. So let me switch back to the questions here. So this was the question we just did. That's also interesting. Will we have the derivatives of the inverse trigonometric functions and the inverse hyperbolic functions on the formula sheet for the exam? Now, you may not have seen this yet, but we put up all the exams. So let me go there now. Let me go to, let's see, calculus. Okay. And then we go, if you go here at the very top of the page to study materials, so if I click that, then you see that where we put the old midterm tests, this list has become a little bit longer. And as you see, we also now have here the final tests for 1920, so that's last year, 2019 till 2020, plus the answers, the resits. So this one, as you can see, was in November, this one in January. And we have also put them there for 2018, 2019. So for the last 2 years, the most recent final tests plus the resit you have now, and you can practice them. As you also see, there are solutions here. Now, we put them there so you can see how to solve the questions. But please try to do the test first before you look at the solutions. I mean, You probably heard this a zillion times before in different courses and in high school too, but try to do it yourself and then look at the solution to check if you did it all right, or if you really have got no clue how to get started. But do not start with looking at the solutions, because that doesn't help you at the final test, because then we don't give you the solutions and you have to come up with it yourself anyway. What is also good is if you start preparing for the final test, to try and time yourself. So these final tests are 3 hours. So arrange your desk, make it completely clean. Just have pen and paper and the questions for one of these tests, and try to do it in 3 hours. Just to get a feel of how much work it is, how much time you need, how you have to plan your time. Also, we will come to that next week during exam preparation, but it also makes sense to not necessarily solve the questions in the order we ask them. So if you see a question and you blank, you have no idea how to solve it immediately, but you see that the next question you have a pretty good idea because you studied that better or whatever, or more recently, just solve the questions that you're pretty sure about first and then go back to other questions later. So you can solve them in any order you want, and that can also help you. Okay, so let me go back now and hope that there aren't too many new questions, because I think now we get a new overview. So we are industrial design. This is week 7. And then we are going to the questions before the lecture. And let's close the menu on the left here, then we have a bit more space. Okay, corrected grade, question. I forgot about that. The reason I just showed you the old exams, in the old exams you see the list of formulas we give you. So in the old exams there is the formula sheet, and that's going to be the formula sheet that you'll have during your final test too. So then you precisely know which formulas are in there. Okay. Then in chapter 3.6, yes, we learned how to sketch a curve. We did that. We have to use the second derivative test to see where the graph is concave and down and what are the inflection points. Well, if you look at the way that I covered section 3.6, I didn't do the inflection point and I didn't do concave, convex. So for curve sketching, you don't have to include that. So the theory is from chapter 3.5, which you do not cover, so you don't have to learn that. And if we ask you to sketch a curve, if you look in the old exams, we hardly ever do. But the main idea is that you should do a little analysis of a function. So the recipe that I gave there, where does it cross the axis, find the derivative, compute asymptotes, all those skills you should be able to do. So that is what's being asked of you for curve sketching. There is a recipe in the slides. Follow the recipe and know how to do the individual parts of that recipe. Okay. When you want to compute a limit using L'Hopital's theorem, a condition is that the limit has the indeterminate form 0 over 0 or infinity over infinity. For me, it was not really clear if there were more conditions apart from this one you should look at. Not really. The other thing is that you're going to differentiate. So you have numerator over denominator. You're going to differentiate the numerator and differentiate the denominator. So there should be functions that you can differentiate. There should be sufficiently nice functions. Of course, all the formulas that you get, like with sine and exponential, etc., they are. So that's normally covered. So yeah, finding that it's 0 over 0 or infinity over infinity, that is the important step here. How do you calculate the antiderivative of 4 over 5 plus 2x plus x squared? Okay, let me do that on my iPad. So I'm going to switch to my iPad, otherwise I forget about that and you cannot see what I'm writing. So let's go there. Let's get some new paper here. Okay. So the question we have here is how to integrate. How to integrate, and the function was something like 4 over, what is it? 5 plus 2x plus x squared dx. Yep. Okay. The idea that you should have here is that this kind of resembles one of the standard integrals in the list of integrals that you get during the exam. Because, well, if you have x squared plus 2x plus 5, you could write that as x plus 1 squared. And if you get rid of those brackets again, it would be x squared plus 2x plus 1. But there is a plus 5, so I can write it like this. This is the same. So now the equal sign holds. And hence we have for the integrand, the function we're trying to integrate, that we can write it as x plus 1 squared plus 4. If you now divide all the terms by 4, we get 1 over, and I'm going to swap the two terms in the denominator, x plus 1 squared over 4. And 4 is of course 2 squared, so I can also write this as 1 over 1 plus x plus 1 over 2 squared. And then maybe you see that this looks a lot like a arctangent function. In the meantime, I'm going to stop Microsoft Teams because I get messages there and that's annoying. So this is something like the arctangent of x plus 1 over 2. Because we have in the table 1 over 1 plus x squared. The primitive function for that is the arctangent. So this is something like the arctangent of x plus 1 over 2 with a little compensation there, because if you do the chain rule, you would get a half, so you have to compensate for that. But the idea is that this is an arctangent. Okie doke. Next question. So I'm switching back to Canvas. Canvas is here. Can you explain question 29? So that's finding the antiderivative of, and then a horrible expression. Let's go back to iPad. So what we have here is now we're being asked for the integral, and then we have 1 over square root 1 plus square root of x dx. Now, this one is not immediately clear. Very often when you have an integral and you've done integration by substitution, integration by parts, when you study those techniques and solve problems with them, you get a bit of an understanding of what's going to work, what's not, and what it will turn out to be. This one is not immediately clear, but what you should immediately try here is substitution, because we have 1 over the square root of something, and oops, the something is this here, 1 plus square root of x. So what you should try here, try integration by substitution. And you have to choose what to substitute. So what you're going to do is whatever is under the square root. So, because then the integrand is going to be something like 1 over square root of u, or u to the power minus 1/2, and we can integrate that. But the dx part is not immediately clear here, because what we have is that du dx, if you differentiate, well, that's 1 over 2 times the square root of x. And if you look in the original question, well, there is no square root of x there, no loose square root of x that we can use to get from dx to du. So the trick here, and this is something that you should see, or you should have seen once, and you see me do it now, is from this here, we have that apparently the square root of x is u minus 1. So what that means is that I can write this here as 1 over 2 times u minus 1. So apparently we have that du is 1 over 2 times u minus 1 dx, or alternatively 2u minus 1 du equals dx. So the dx that we have in our original integral, we can replace with this here, 2 times u minus 1 du. And then you can write the whole integral in terms of u, do the integration, and substitute back. So if you want to know the general layout of this question, we have an integral. We do integration by substitution with the u choice that is given here in this circle. And then there is a bit of fiddling around, but that is the main step. And then if you do it carefully, everything will turn out to be okay. But you do have to see that you have to replace the square root of x by an expression with u. So that is the new thing here that is not immediately clear, but now you've seen it, so hopefully in future examples you know how to do this yourself. Okie-doke. Going back to Canvas. So at high school I learned that if fx is ln x, then this is a primitive function, x times ln x minus x, as a standard primitive. I had learned by heart. So you can use that during the test, but it makes sense to explain why this holds true. So I would just write a few lines of text there and say, I know this by heart, and it's correct because if you differentiate my capital F, you get ln x. So basically what we want to see during the test is that you did not cheat and did not get the answer from the internet, a friend, your textbook or whatever. But if you say, well, I know this holds true because I learned it in high school, or I know this holds true because if I differentiate, then I get the ln function, I know this antiderivative, then it's okay, then it's fine, then you can use that. That's also something, maybe a couple of you have already seen it in the midterm test. There was this question where you had to go from a vector equation of a plane to the normal equation with ax plus by plus cz equals a constant. And many of you did it in a different way because I do it in a different way than it was in the answers there. So that's perfectly all right, and you get a full score there if you wrote it out correctly. But it's just a different way. So if you do things in a different way, that is fine as long as it's mathematically correct. Okay. Could you give an example with Riemann sums evaluation points? There are a couple of questions about that in the homework. I'll give an example. It's not that interesting what's happening there, but maybe for the understanding, it's good to do a little example. So I'm going to make up an example. So let me switch again to iPad. So a little bit about Riemann sums. So for instance, say that we have the function f of x is the exponential function e to the power x. So as you know, that looks like this. Y is e to the power x. And let's say that we're going to look at this function on the interval from 1 to 5. And we would like to approximate the integral from 1 to 5 e to the power x dx. So what you can do is, for instance, cut this interval into 4 equal parts. And of course I chose the numbers nice. And if you then on each of these sub-intervals, so every sub-interval has width delta x, which is 1 here because that's how I chose it. Let's say that we choose the midpoints of these intervals. So the midpoints are here, right in the middle, here, right in the middle, here, and here. So this value would be 3/2 because it's in the middle of 1 and 2, so that's 3/2. The second red cross that I drew here, it's 2.5, and 2.5 is 5/2. The third one in between 3 and 4 is in between 6/2 and 8/2. So this is going to be 7/2. And then the last one is 4.5, and 4.5 is the same as 9/2. So you could approximate the area under the graph here, or the integral if you like, by computing f at 3/2 times delta x plus f at 5/2 times delta x plus f at 7/2 times delta x plus f at 9/2 times delta x. So this number, if you compute it, is an approximation to the integral. And basically what you're doing then is, if you look at the first interval, you look at the area of this bar here. So this is a bar and the width is delta x, which happens to be 1 here. And the height is the function value in the middle, so the function value at 3/2. If you take more of these intervals, you get a better approximation. If you let the number of intervals go to infinity, so the width delta x is going to 0, then you get the integral. So that's the idea of these Riemann sums. So hopefully that's sufficient explanation for the question on Canvas. If not, let me know and I'll happily come back to it on Monday. So going back to Canvas, nearly there. This is an example with probably incorrect numbers, but it's about the idea. So we have the log of x plus 5 plus the log of x plus 2 equals 0. You're trying to solve this. And the basic question is x equals minus 6 a solution here? It is not. So if you have an equation with, for instance, logarithms or square roots, and then you do a bunch of stuff in between and you find some solutions, you should always check at the very beginning by substituting if they still hold. So if you would find x equals minus 6 and you try to plug that into the original equation here, you see, for instance, for the first term that you get a logarithm of minus 1 that is not defined. So you cannot substitute x equals minus 6 into this equation, so you have to reject it. It is not a solution because the logarithm of minus 1 is not defined. So that's the way this works, and a similar thing holds with square roots. So by doing steps in between, it can happen that you introduce extra solutions, and you always have to check them at the end. So at the very end, you check whether they indeed solve the original equation or not. And that brings us to the end of the questions. Excellent. So I am going to click on the little plus sign at the top to show that we have answered these, and a new round of questions can start. Yep, okay. And we have a clean sheet again. So keep those questions coming, put them up for Monday. Wednesday, sorry, it's Monday today, and we still have Wednesday. So if you have any questions, any doubts, any things about the homework that you cannot discuss with your tutor for some reason because there is no time or whatever, let me know, and I'll happily try to answer them during the lectures. So I am going to go to, let me try this here. Excellent, that works. So about the lectures for this week, what you see here is our solar system, and our solar system you can describe using differential equations. So today we will probably not be talking about differential equations yet, but we will be on Wednesday. There are many things around us that you can describe, especially if they have to do with forces, acceleration, velocities, and so on, using differential equations. And for instance, the movement of the solar system can be captured into just a couple of mathematical equations, which is really strange if you think about it, that something as large as the solar system and the planet movement, which is very complicated if you think about it, but you can write that down in only a few mathematical equations. So we will get there on Wednesday, and I will show a couple more fun examples too. So let's see, what do we have planned? So in the book, we will be talking a little bit about sections 5.4 and 6.6. That's the last bit on integration. And basically what we're going to answer is, what is the length of a curve? So if you would have the curve of a function and you would be walking along it, what is the distance that you travel? A little bit about surface area. So if you have a function, you rotate it around the horizontal axis, you get an object. What is the area of that object? And differential equations. And we've got a bunch of applications, as you see here. So let's get started here. So the first question, what you see here is a piece of rope. Now, if you think about the length of a piece of rope, the way you would do that is basically what you see in this little animation. So if you have a piece of rope, what you would do is you grab it at the end points and you pull to make it a straight line, and then use a ruler to measure it. So here the light and dark segments, they indicate the length of this piece of rope. And as it says here in the text, this is an animation. So if you download the PDF and you would like to see this animation too, depending on the PDF viewer that you use, you can see the animation, or maybe you cannot see it. If you use Acrobat Reader, you should be able to see it. Now, the question that I would like to answer now is, how would you do this using mathematics? Because taking the ends and stretching it, that makes intuitive sense, but mathematically that's very difficult. To have a graph and then stretch it, that is hard to capture using the techniques and the functions that we have seen so far. Still, this is an interesting question. For instance, if you have some copper wire and you have a certain shape and you would like to know how much copper wire is very expensive, as you may know, you would like to know how much you need there. So let's say that we have a simple function, the sine function, and now what I'm going to do is I'm going to start in the origin and I'm going to walk along this curve, and I would like to know what distance did I travel for when I reach the end point, so x equals pi here. Maybe you already know the answer here, but if we would like to actually answer this question mathematically, we would proceed as follows. So what we do is we take this graph and we are going to cut it into 2 bits here. So it says here n equals 2. And what I am going to do is approximate the length that I would like to compute, basically with 2 straight lines, or line segments would be more correct, because a line stretches on infinitely and here it has 2 endpoints. So a line segment. So what I try to do is find the length from here to basically halfway, and this length, well, that's just a bit of straight line, so I can easily compute that. Or I could take this point here, I could take this point, and then compute the distance between 2 points, and we've already seen how to do that. And then I also do the length from here to here by joining the two with a straight line and compute that. Now, as you see from this graph, this is an approximation, so it gives some indication of what the value will be, but it's not going to be very accurate. But then again, we have been talking about all these kinds of limiting processes, and you can immediately see how you can get this more accurate. Because if I do not take 2, but instead I take 4 black line segments, so I go from 0 to x equals pi over 4 and the corresponding y value, and then I go from this point to the middle, and from the middle to this point here, x equals 3 pi over 4, and then finally from 3 pi over 4 to pi. And if I add those 4 line segments, the lengths of those 4 line segments together, you get a better approximation. And you can also do that with 8. And here you can hardly see the red graph anymore, so it already gets pretty accurate. And you can do that with 16, 32, a million, whatever. And of course, what we would like to do mathematically is let n, the number of line segments, go to infinity. And then the distance between points on the horizontal axis. So here it was pi over 2. Here the distance is pi over 4. Here the distance is pi over 8. We let that shrink to 0. And the approximation we get is better and better. Now, to get a formula there, I'm going to need a theorem. So this theorem, I would normally not give it here, but since I want to derive this formula with you here, I mean, we've done so much mathematics in the past weeks that we can actually find a representation, a formula for the length of the curve. So I'm going to derive that with you. So let's say that we have some function f. So we have an interval from a to b, and I'm going to present to you the mean value theorem. So what does that say? Well, it says that if you take this point on the graph and this point on the graph, so I labeled them A and B, and you draw a straight line through them, so the black line that you see here is just a straight line through these 2 points. Well, then of course we know the slope, right? Because we know what the slope is. It's the difference in y values, delta y, over the difference in x values, delta x. So what it is fb minus fa over b minus a. We've seen that in week 1. That's old stuff. Now, what the theorem tells us is that you can find some point in between a and b, and if you will draw the tangent line to the graph at that point, it has the same slope. So for instance, if you're about here, and here you will draw the tangent line, you see that it is parallel to the black line. So apparently the derivative at this point, so this point here I could call C, then we know that f prime c, that's the derivative of the red dashed line, is the same as the slope of the black line. If you look carefully, you will see that there is one more point, because around here, if I would draw the tangent line, you see that it's also parallel to the black line. So what the theorem tells us is the following. There is AC in AB such that the tangent line at x equals c, so that's f prime c, has the same slope. So m equals f prime c. So here it is in a theorem. If we have a function that's continuous and differentiable, so continuous on the closed interval, differentiable on the open interval, because we need a little bit of space to the left and to the right to talk about differentiability, then you can find a c such that f prime c equals fb minus fa over b minus a. So that is basically m, the slope of the black line. Now, note that it says there is such a C, not that there is precisely one such a C. As you can tell from the graph already, there is a C here, but there is also one there. So here in the graph, you already see that there is two of them. There can be many more. So there is at least one C in the interval such that f prime C equals the slope of the black line. And maybe more of them. So I will be using this mean value theorem to find a formula for the length of a curve. So if we go back to what we had before, so here we have a curve, it's hard to see, but below here there is a red curve. I try to approximate it with these little black lines. So here apparently I drew 8 of these black line segments. The points Pi are the points, well, here and this point and this point. So they're all points that are on the graph of the function and so on. And every 2 neighbors I'm going to connect by a little black line segment. So Si is the line segment from Pi minus 1 to Pi. And then we can approximate the length of the curve, so capital L, with the sum of these lengths here. So if you take S1 plus S2 plus S3 plus S4 and so on plus S8, so all of those lengths, if you take them all together, you get an approximation for the length. What I'm going to do next is find a formula for Si. So how can we do that? Well, the length of Si is the distance between the 2 endpoints. For the 2 endpoints, I know the coordinates because the coordinates are always xi, fxi. So what we have is that it's the square root of the difference between the x coordinates and the difference between, well, delta y it says, so the difference between the y coordinates, which is fxi minus 1. And now I'm going to do some basic stuff with this. If you don't know where it's going, then it's not entirely clear why I do these steps. But the separate steps are not going to be very difficult. So what I do first is I'm going to pull out this factor, which means that I get a 1. And for the second one, if I pull it out, it means that here I put it in the numerator, so here it should also be in the denominator. Why do I do this? Well, this here, that looks a lot like what we have seen on the previous slide in this mean value theorem. So apparently I can find a Ci that is in between xi minus 1 and xi, for which whatever is here in between these parentheses equals f prime Ci. So that's the last step that I'm going to do here. So I'm going to say, well, I'm pulling out one of these, so I write it in front of the square root. And then this here in between the brackets, I replace with f prime Ci. Still pretty ugly, but we're almost there. So what we get is called the arc length. So the arc length is if you walk along this function here, what is the distance you travel? That's called arc length. In Dutch language, it's called booglengte. So I'm going to cut this interval from A to B into a number of subintervals. And every little subinterval here, all of them have the width delta x. And then the points here are going to be, so this is going to be x0, this is x1, x2, up to xn. So I label the endpoints of each little subinterval. And then I can approximate the length, the arc length. So the length, if you travel along the graph from A to B, I can approximate that with ln, which is the sum of all these little black line segments. So this is the formula that we found on the previous slide. Now, hopefully you see or you recognize by now that this is a Riemann sum. So if you now let the number of terms in this sum go to infinity, which means that delta x will be going to 0, you get an integral. And that is the last bit. So the arc length L of y equals fx on this interval AB, that is the limit for n going to infinity. And if you take the limit for n to infinity of this sum here, you get an integral. And the integral is going to be the integral of the square root 1 plus f prime x squared. Let's have a little break here for now, because it's already past quarter past. I'm going to continue at 2:30, so we have a 10-minute break to grab some tea, coffee, or whatever, and I'll see you in a bit. So let's start again. Before the break, we have derived this formula here for the arc length. So given a function, what is the length if you would start here at the point A, f of A, and walk along the graph to the point B, fb? And we have seen that you can write that as an integral. So this is one of the integrals that you will find on your formula sheet. The integral from a to b is square root 1 plus f prime squared x dx. As you can probably imagine, if I give you any non-trivial function f, so a function that is a little bit complicated, then first if you compute the derivative, f prime, it's probably going to be an even more difficult expression. And then if you square that, do plus 1 and take the square root, probably that's going to be a pretty horrible function to integrate. So finding an antiderivative of what it says here in this integral, well, the chances of success there are going to be pretty limited. Now, there are functions for which you can actually evaluate this, but they're kind of special. Now, what is nice to see is that one of the shapes that we have encountered earlier, the catenary, so if you have a chain that you support only at the endpoint, and then as we have seen, the shape you get, which was something that Gaudi used in his designs, is a cosine hyperbolic function. And that is one of the functions that you can actually integrate. So let's look at an example there. So say that we have two poles. So here is a pole and here is a pole. They are 6 meters apart and we hang a chain there. Now, what is then the length of the cable of this chain that you hang there? It would seem that you lack information here, but you don't. Because what we know is that the shape it assumes is going to be this catenary shape. So we know that the shape of the graph that you have here is 3 times cosine hyperbolic x over 3, where x is ranging in between -3 and +3. Okay. And then with what we have just seen with the formula for the arc length, apparently the length of the cable, so capital L, is the integral from -3 to +3 and then square root and this whole thing here. Okay. So let's see what we get for this function here. So if we have f of x is 3 times cosine hyperbolic, then f prime is going to be a sine hyperbolic function. But as I told you when we were discussing these functions, you can either try to remember all these formulas by heart, the relations between sine hyperbolic, cosine hyperbolic, and so on. What I prefer to do is go to the definition, so go to the exponential functions. So in particular, for this situation, so this is just a question restated, we have that the cosine hyperbolic is the exponential of e to the power x over 3, e to the power minus x over 3, divided by 2. So I wrote that in front of it. Then if you differentiate, that's easy because the derivative of an exponential is that exponential. And then with the chain rule, we have an additional 1/3. So what you get altogether is this here, and this is a sine hyperbolic if you maybe you recall that. But I'm not going to use that here. Now, what is also special, we haven't seen that yet. That's kind of new. Is that this here? So the whole integrand, the function that we need to integrate to find the length, that's going to simplify quite a bit. Because let's first compute whatever is under the square root sign. So 1 plus f prime squared. So if I do that, I plug in f prime as we have just found it. Getting rid of the parentheses here, I get 3 terms. And e to the power plus something times e to the power minus that something is going to give 1. So that explains the -2 that we have here. And then if you take these all together and you get rid of the bracket, so you expand everything, we have what it says here. And then there is one additional step, because you have to recognize that you can write this as a square again. So what I do is I pull out a 1/4 and then note that you can write it as this thing squared. Why do I do that? Well, I need to have the square root of the whole thing, and the square root of a square, as it says here, that's easy to find. So apparently the whole integrand with the square root, well, that's the square root of the expression we just derived. This one you can actually compute, because the square root of 1/4 is 1/2, and here the square and the square root just cancel. And then, forgetting everything that we have seen so far, if you just look at what it says here, well, this is pretty easy to integrate. So let's do that. Then we have this exponential minus this exponential with these two limits. Plugging them in, that's basic, I'm sure you can do that. You find this expression here. Now, if you recall that E equals something like 2.7, if you punch this into a calculator and you see what the value is, then you will find that the length of the cable is a bit more than 7 meters. So that makes sense, right? Because we had two poles and they were 6 meters apart. Of course, this chain, this cable is hanging a little bit, so we are going to need more than 6 meters. So 7.05, that makes sense. That's a reasonable value. So this is how it works, and you will find in the book there is a couple of more questions about arc length, as it is called. Now, what I quite like about this example, and hopefully you appreciate that too, is that basically with the mathematics that we have seen in the past weeks, we could find a formula, this formula here, so the arc length formula, for the length of a cable or of a graph in general. We can do something similar for area. So what we are going to do is take a function like here. So we have a function y is f of x, and let's say that it's positive, so it's above the horizontal axis. And now we are going to rotate it around the horizontal axis. So we're going to swap this around, and what we get is a shape like this. And if you change the viewing point a little bit, it is a shape that looks like this. And the next problem that we're going to tackle is, can we compute the area of the shape that we have this? So here we have a bit like a trumpet shape. And can we compute the area of this trumpet? So that is our next question. Now, if you follow a bit along the way of reasoning that we have done so far, what you can probably expect is that this is going to be quite hard to have this area in general. But if we would have a straight line here like this, and then we rotate it around, you have something like a cone, a bit like a road cone. And for a cone, we can't find the area. And then what we're going to do is we're just going to break this into little straight line segments and use those. So that's the idea, and we're going to derive again an integral to find this area. So how do we do that? Well, first we're going to break it into 2 points, and then this is a straight line that is being rotated, and this is a straight line. If you want it to be more accurate, you have to use more straight line segments. So here it's 4, so this is a straight line, this is a straight line, this here, and this here is also a straight line, and then we rotate it around. And you can do that if n equals 8. And of course, in the end, what we are going to do is let n go to infinity, and then we have an integral rather than a sum. So now we have a sum as an approximation to the surface area, and then we will have an integral. So as a bit of extra, we need the area of a cone. So this here is a cone. So if you take a piece of paper and I have a piece of paper here with nice musical notes, and if you make a cone like this, and if you flatten the bottom, that is a cone. So like you have on the side of the road, the orange things in the Netherlands, when there is roadworks, that's a cone. The area of a cone, of course, you can find on Wikipedia or whatever what the area is, but let's try to find the formula here ourselves. So what I did is first introduce a little bit of notation. So if you have a cone, then basically the size of the cone you can describe by two numbers. One is the radius of the base. So if you have a cone and then you take the base like here, so there is like a circle here, and that circle has a radius. So that radius is little r. And then what you could also do is you could, if you have a paper one, you could cut it open along a straight line. So from the top straight down. And that length is called the slant height. And I'm going to call that L. So if you make a crosscut, here is the half of a crosscut. And basically, well, this would be the true height here. But this is the slant height. And this is the radius of the base. Now, to get to a formula for the area of this thing, and the area of this thing is only what you see here, so the bottom doesn't count here. The bottom is open, so it's only the side of the cone that we're going to compute the area for. So what I'm going to do is, indeed, I'm going to cut it open along this black line here, and then I'm going to put it flat on the table, and then you would have something like this here. So the cone itself is the darker shaped area here. And just to make clear that it's part of a circle, I also put here in light ray this little bit, but that is not part of the cone. That's missing from a full circle. Okay? So if you would have the full circle here, it would be a circle with radius little l, and that is area pi times l squared. Now, we don't have that completely, so what we have is theta over 2 pi. So theta is the angle that you see here. So we have the theta over 2 pi part of this. Yeah? If theta equals 2 pi, we have the whole circle. If theta equals pi, we have half the circle, and so on. So to get to a bit of a different formula, because in this formula, this is in principle okay, but there's a theta in there, and I described my cone with r and l only, so I don't want theta to be in there, and I can get rid of it. So how can you get rid of it? Well, what you could do is you could look at this base of the cone here, and then the circumference. So if you look here, the circumference is 2 pi little r, because little r was the radius of this base circle. On the other hand, if you look at this picture here, then you see that the full circle here has circumference 2 pi l, and again we take the theta over 2 pi part of it. So this equality holds. So if you just compare those two, you can divide by 2 pi if you like. You see that L times theta over 2 pi equals R. Then going back to this formula, I can also write that formula as pi times L times theta over 2 pi. And then this bit here apparently equals little r. So now we have found that A equals pi times L times R. So this is the area of a cone if you describe the cone with these two numbers. So little r and L. So I'm going to make use of this in a little bit of time. This is not the main goal. This is getting towards a general formula for surface area. So here on the slide, we have that the area that we're looking for is pi times r times L. Now, I don't want the area of a full cone, because if you think about a function, and I'm going to cut that into bits, and then I'm going to have these line segments, and I'm going to rotate the line segments around the axis. So what I need is not a full cone like this, but a slice of it. So let's extend our derivation a little bit and cut off the top part of the cone. So here is the full cone, and now I'm going to cut it into 2 bits. And I'm particularly interested in finding the area of this bit here, because when I'm going to a general function and approximate it with little line segments, I will have all kinds of slices like these. So what is the area of this slice? Well, I can make this helpful drawing. We have a base radius R1 for the top bit. We have a base radius R2 for this one. slant height L1 for the top bit, and L1 plus L2 for the full cone. Now, with what we have already seen on the previous slide, we know that the full cone has area A1 plus A2, and that is pi times the base radius, which is R2 in this situation. The slant height is the sum of these two, L1 and L2. Okay, that's great. Then the top bit, well, that has this area, that's a full cone. So the bottom part, well, that's the difference between these two areas. So I can just subtract them. And then I find this formula, but I'm not completely happy with this formula yet. The reason being that if I just specify the bottom bit here with these three numbers, R1, L2 and R2, that I don't want a formula that involves L1 here. I don't like that. I don't want that. So here you need a little bit of trigonometry. So you have to look at these two triangles. So we have a triangle, so the top bit here, and then we have the full triangle. And as you see, they basically have the same shape, right? So they are similar, as it is called in trigonometry, in geometry. So then the ratio L1 over R1, so this length over this length, should be the same as this length over this length here. And then you rewrite a little bit and you have this green formula and you plug that in, rewrite a little bit, and then we have the following for the area of a slice. So maybe this is a bit fast, but I just want to show you that with basic geometry, nothing special is going on here. If you give sufficient information, you could ask this from a high school student, pupil. What we have is this formula. So the area of this bottom part here is apparently pi, it's popping up again, R1 plus R2 times L2. So L2 is now this length here. Okay. And now we have all the bits and pieces and we just have to put them together like I did for the arc length. So again, we're going to derive an integral here, but it's of course going to be a little bit different. So here I cut the interval, so I'm going to look at the function from x0 to x4, so that's my interval AB. I cut it into 4 equal bits, so every bit here has width delta x, like we did before. And on every interval I'm going to approximate the function with a straight line. And if you then rotate the straight lines around the horizontal axis, you find 4 slices of cones. And then the surface area of the graph can be approximated with the sum of those 4 areas of the slices of cones. Now, slice I is formed by rotating from pi minus 1 to pi, so that is very, very similar to what we have seen for arc length. And then you see that these two radiuses here are the function values. And then the L2 of the cone, that is precisely d pi minus 1 pi, the distance between those 2 points. And we have derived previously, during the arc length derivation, we've called it SI, and that was equal to this expression here. So now we have all the bits and pieces. So we see that apparently the area of one of these slices is the general formula for a slice of a cone. And then we're going to substitute the expressions that we had before. And I am going to say that fxi minus 1 plus fxi is approximately fci times 2. So basically what I do here is that I say, well, fci, so ci is the point from the mean value theorem, where we have this f prime here. I'm going to say that this is approximately fxi minus 1 plus fxi over 2. So basically, I approximate the function value at that point ci, that is somewhere in this interval between xi minus 1 and xi. I'm going to say that the function value there is approximately the average of the function values of the two endpoints. And if you make this interval smaller and smaller and smaller, this is going to hold, because then the function is going to be, well, almost constant if you have a very, very small interval. Okay. So what have we seen now? If you have a function, general, continuous, differentiable, blah, blah, you cut the interval into n subintervals. The surface area can be approximated with the sum, and this sum is just the areas of the slices, as we have found on the previous slide. And then if you increase the n, the approximation gets better. If you take the limit of n going to infinity, you find an integral. So that's the definition, surface area. If you revolve the graph y equals fx about the horizontal axis, so you have a function, you take the horizontal axis and you rotate it around, that's the idea. Then the resulting surface that you get, that's called the surface of revolution, because you turn around, equals 2 pi times integral from a to b fx times square root 1 plus f prime squared dx. So if the integrand for the arc length was already complicated, you see that this is basically what we had for arc length, and now there is even an additional fx there. So this is often very, very difficult to compute. And only for very special functions f, you can actually compute the surface area. So I will present you with an example in a second. And before I do that, I look at the chat room. There was a question on doing exercises from the homework. I will do that on Wednesday, because now I didn't prepare and I would have to look them up, and that's going to take too much time, but I will do them. And then Sam asks what the FCI means in all these derivations. So the CI is the CI from the mean value theorem. So in the mean value theorem, we have seen that, let me write that down here. We had that f xi minus f xi minus 1 over xi minus xi minus 1 equals f prime ci for some ci in the interval xi minus 1 xi. So the CI from the mean value theorem, that is the CI that you see on all these slides appearing. Now, as I said, in general, this is going to be a pretty horrible integral, and in special cases you can actually find an antiderivative. If you cannot, you would have to use, for instance, Riemann sums to approximate the integral numerically. So you cut it into subintervals and take those. So you do something like this with finite n. But here we will do the integral. And here is first an example where I would like to just try and get some confidence into this formula. So we did all these derivations, and of course they're in the book, so they're correct. You can trust me on that. But if you do that yourself and you would like to understand, like, well, does it make sense what I've been doing? Does this hold true? You can try for a simple case to see if the formula works. So that's what I'm going to do here. So I'm going to take the function y is fx is x plus 1, so a straight line, like you see here. And I'm going to rotate that around the horizontal axis in between x equals 0, x equals 1. And I'm going to find the area there. Now, this is just a slice of a cone. So I can use that formula, and that's going to be method 1 here. So method 1 is use the formula for a slice of a cone. So we can use this formula here. The two radiuses are, well, this height, which equals 1, and this height, which equals 2. So that's the 1 and the 2 that you see here. And then the slant height, that's the length of this bit here, Well, that's from the point 0, 1 up to 1, 2. So you see that it's like the diagonal of a square with side 1. So that is the square root of 2. And then apparently if you plug that into the formula, you find that the area is 3 times pi times the square root of 2. Okay, that's one. The second one is that we say, well, let's use this formula for surface area that we just found. And that's coincidentally also one of the formulas that you will find on the formula sheet at the exam. So you don't have to learn this by heart. Now, the boxed formula here should, of course, give the very same result. So this should also give 3 times pi times the square root of 2. Because, well, how you compute it shouldn't matter, right? You can choose the way that you like. So let's see. For the formula, so our function is x plus 1. If we differentiate that, we have f prime equals 1. And the limits of the integral are 0 and 1. A equals 0, b equals 1. If we plug all that in, then we see that apparently a should be 2 pi times the integral that you see here. The square root of 2, that's just a constant, so you can write it in front of the integral. X plus 1, if you take a primitive function, you find half x squared plus x. And then if you evaluate that at the two endpoints, you find indeed 3 times pi times the square root of 2. So that's nice. We find the same result, so as it should be, of course. I'm going to do one more example, which is sometimes you have these mathematical stories or mathematical paradoxes. So nice stories, but they seem to be contradictory. This is one of them. It's called Gabriel's horn. And Gabriel here is the archangel. And as you may or may not know, he blows his trumpet. And here we are going to look at something that looks a little bit like a trumpet, but it's an infinite one. So that's why it's called Gabriel's horn, because an infinite trumpet, well, that cannot happen in real life. So what we are going to do is look at this function. Y is 1 over x. And we are going to consider that, well, basically from x equals 1, and then x is going to go to infinity. So it's going to go down and it's converging towards 0. Of course, it will never reach 0. Only the limit for x going to infinity equals 0. And if you rotate this function around the horizontal axis, then you find a trumpet shape like you see here on the right. Now, I have been talking about the area all the time. You could also consider the volume. So for the volume, I'm not going to derive the formula, but maybe you already had this at high school. Otherwise, you can look it up in a book. So what you could look at is the volume of the horn, and then I'm going to consider it from 1 up to some number capital R. So capital R is going to be a number bigger than 1. And then the volume, well, it's pi times fx squared, and then you have to integrate. So this is a little bit like if you have a cylinder, so you see it as a bunch of cylinders. Now, if you plug in the function, so the function is 1 over x, then we get a 1 over x squared here. We can integrate that, and the primitive function is minus 1 over x. We plug in x equals r, x equals 1. And then what we find for the volume is pi times 1 minus 1 over capital R. So if I let capital R go to infinity, then this thing is going to 0, and we see that the volume is going to be pi. So what that means is this shape, form, trumpet that we cannot build because it's infinitely long, but the volume goes to pi. So if you would take paint and you would pour paint into this trumpet, then apparently if you put in pi liters of paint, it's going to be full. Okay. Next, I'm not going to fill it with paint, but I'm trying to paint it. And I would like to see how much paint do I need for it. So what is the surface area? Now, for the surface area, we have just found a very nice formula, which is here. And here it will turn out that even for this pretty simple function, we cannot actually compute it, because if we plug in the function, so the function is 1 over x, the derivative of 1 over x is minus 1 over x squared, so minus 1 over x squared, and then we have to square it again because there is a square root of the f prime in the integrand. So then we get 2 pi times this integral here. Now, as you can probably imagine, it is not very easy to find a primitive function here. If you would have to find a primitive function, well, you could maybe try substitution or integration by parts. But what I would like to do here is just give an estimate. So I'm going to say, well, the function I'm integrating here, it is always bigger or equal when I replace what it says here with a 1. Because it says 1 plus 1 over x to the power 4. 1 over x to the power 4 is something positive. So if I just delete that, I make it a little bit smaller. So it's bigger equal, and then the integral where I just forget about this whole square root, or I replace it by 1 if you like. So then you have the integral of 1 over x dx. Now, the nice thing is I can find a primitive function because that's the ln. Then you plug in the values, r and 1, and you find that apparently the surface area is 2 times pi times ln r. And now something strange happens. Because if I now let r go to infinity, you know that the ln of x for x going to infinity is also going to infinity, very slowly, but it does. So this goes to infinity for r going to infinity. So apparently the trumpet that I have here has a finite volume because this integral goes to pi, but the area is going to be infinite. So I can fill it with paint, and I need pi liters for that, but I cannot actually paint it because the area goes to infinity. If that is confusing to you, there have been many texts about this, and many people have thought much too much time on this, but it's a nice example where you see how these integrals work. So the next topic is improper integrals. Before I go there was a question. So Lieke wants to know if you only have to know the formula for arc length or also the derivation. So basically, how did I get to this integral? You only have to use the formula. So at the exam, you will actually be presented with the formula, and we can ask you like, well, this is our function f of x. Consider it on the interval from 2 till 7. What is going to be the arc length? And then you just have to compute the integral. So you don't have to know the derivation. And if you think about it, then I think that probably if you look at the derivation, we're not going to ask you to do that. But hopefully you do understand the in-between steps, because I think the in-between steps, they don't use more mathematics than we have seen so far. But you should, it is not necessary that you could do the derivation yourself. That's absolutely not the goal here. So the goal is to be able to use it, to be able to compute an arc length or a surface area for the second part of today, but not do the derivation. I present the derivation because I think it's nice that with the mathematics we have seen that you can find these integrals. So that's the reasoning behind it. A little bit about improper integrals. Improper integrals, it is not terribly interesting. It's just a bit of naming and writing things down correctly. So sometimes when you have an integral, funny things can happen along the way. That's basically what improper means. So what is that? Let's look what can actually happen. So if improper behavior for a function means that it goes to infinity or minus infinity or stuff like that. So I have 5 cases. The first one is that at the left point of your integration integral, so for x going to a, but from the right, Your function goes to plus infinity, as I have shown in this picture, or it could also go to minus infinity. So if your function goes to plus or minus infinity at the left point of your interval, we call this integral, we call it improper. And how to properly deal with that, I'm going to show you in a second. But first I'm going to list the cases of an integral being improper. The next case, if it happens at the right point of the interval. So we are talking about the interval from a to b. If you approach b from the left or from below, and if your function goes to plus or minus infinity, that's also called improper. Third case, it can happen along the way. So somewhere in the interval, say at a point c that's in the interval, your function goes to plus or minus infinity. That would also be called an improper integral. And then next, if the interval is unbounded, so the right point b is actually infinity. So you are looking at an integral from some constant a to infinity. And then the last, you can probably guess what it is, case 5, if a equals minus infinity. So we're trying to compute an integral from minus infinity to some fixed value. So these 5 cases are called improper integrals. And since strange things can happen, you should be a bit careful in how to deal with them. So what does that mean? It means the following. If you have that your function does not exist at the left, then what you're going to do is you are going to replace this point A with a number capital R, and you're going to compute the limit of capital R going to A from the right. So I'm going to give you an example in a second, but this is how you deal with them in a mathematically sound way. Now, if you can actually compute this integral and then take the limit and you find a number there, it's equal to some number L in R, then we say that the improper integral converges to L. This is just naming. This is just how we call it. And in the other case, if the limit does not exist, then the improper integral diverges. And diverges basically means it goes to plus infinity, minus infinity, it oscillates, stuff like that. Not a fixed number L in R. Similarly, if you have the difficulty at the endpoint B, then you replace B with capital R and you let capital R go to B from the left. Similar terminology, if the limit exists and goes to a fixed number, it converges. If it does not, we say that the improper integral diverges, so that's the same naming. Let's look at an example how this actually works. So here we have the integral from 0 to 1, and then we have 1 over square root 1 minus x. Now, the reason that you have to be a bit careful here is that at the right point, for x equals 1, you see that you get division by 0. So the integrand, the function we're trying to integrate, so I'm not even sure if I ever, but this function that you're trying to integrate is called the integrand. And the integrand is not defined at the right endpoint of the boundary. So here I drew the function, and you see that indeed if x goes to 1, it has a vertical asymptote. It's going to plus infinity there. So how do we deal with that? Well, that's what we just discussed. So instead of the integrate from 0 to 1, I'm going to pick some capital R here, and then I'm going to integrate from 0 to capital R. I try to compute that, and then I let capital R go to 1. So let's do that. So I'm choosing R in between 0 and 1, and I'm considering I as a function of R now, where I integrate from 0 to capital R. Now, we can do this using integration by substitution. You know how to do that. You've seen that technique. du equals minus dx. You can express the integral in u, evaluate. I change the limits here so I don't have to go back to x. And then I find that apparently this integral equals 2 minus 2 times the square root of 1 minus r. And you see that this expression is perfectly well defined for r going to 1. So I can just plug in r equals 1 and I find 2. So the conclusion is that the integral from 0 to 1 is the limit of r going to 1 from the left. So that is the limit of r going to 1 from the left of what we have just found. And we can just plug in r equals 1 and we find 2. So that's how this works. You basically replace the difficult point, in this case 1, with a new letter r, and then you take the limit and you try to compute the integral and then take the limit. So case 3, which is along the way, so in between a and b you have a difficult point. Instead of integrating from a to b, you go from a to c and from c to b. Now this one is an improper integral and this one is an improper integral. So this one has the difficulty at c, which is the end point of the first integral, and this one also has the difficulty at c, which is the starting point of the second integration interval. So you find 2 new integrals, both are improper, and you deal with them as in case 1 or case 2. If your integration interval is infinite, so for instance if b is plus infinity, you replace the integral from a to plus infinity with an integral from a to capital R, and you let r go to plus infinity. If it exists, it converges to L. If it does not exist, diverges. It's the same story all the time. If a equals minus infinity, then you replace the minus infinity here with a capital R, and you let capital R go to minus infinity. If it exists, we say that the integral converges and otherwise diverges. Okay. A little bit more. If you have the function y is 1 over x squared, and you would like to find the integral from 1 to plus infinity, so then we're going to replace plus infinity with capital R. So the integral from 1 to plus infinity is going to be the integral from 1 to capital R, and we let capital R go to plus infinity. We compute this. So we have f of x, that's 1 over x squared, x to the power minus 2, primitive function minus x to the power minus 1, plug in r and 1, the endpoints of the integration interval, take the limit and it goes to 1. So we see here that indeed the limit converges, the integral equals 1. The integral converges to L equal 1. If you try to do the same thing with 1 over the square root of x, we can do the same. So I'm replacing infinity with capital R. This is my integrand, 1 over square root of x. Primitive function 2 times square root of x. And now you see that we have this limit here. So the limit r is going to infinity, 2 times square root of r minus 2. If r goes to infinity, the square root goes to infinity. So we see that the whole thing goes to infinity. So it diverges. Now, since integrands of this type, x to a certain power or 1 over x to a certain power, they occur frequently. We can kind of generalize what we have just seen. If you have the integrand of 1 over x to the power p, with p some number, it will converge for p bigger than 1. For instance, here, this is the situation where p equals 2. And it will diverge for p equals 1 or less. And here, the other example is p equals 1/2. So this seems like a good point to stop. There is a little bit more on improper integrals, but then we also have the Wednesday lectures, and this is maybe a bit technical and a bit boring to you. So try to have a look at some of the questions. Let me know if you do not understand stuff. And I see that Iana asks in the chat room if you have to know the mean value theorem. You're not going to be asked about the mean value theorem. So I needed that for my derivation, which is why I put it in there. But we're not going to ask you any questions about that. It is in the other variants of calculus, so you're lucky there. They do less interesting stuff with, for instance, mean value theorem and also integrating rational functions, polynomial over polynomial. I think those are kind of boring topics. Instead, we do this arc length and surface area, which is much nicer because you're actually computing something that you have some kind of idea what you're doing. It's also of practical value, so I think those are nicer topics. So that is going to conclude the lectures for today. If you have any questions, feel free to send them to me. Preferably place them on Canvas. On Wednesday, I'm going to start once again with going to Canvas and see all the questions that are there and answer them. For now, have a great day. It's sunny outside here in Utrecht, so enjoy a little bit of that. And I'll see you again on Wednesday morning. Bye for now.